Good day everyone, welcome to the official editorial of our CodeForces round. In this video I'll explain the solutions to all problems. Without further ado, let's get started with problem A. In this problem we are given a number n that is between 1 and 100, and we need to construct a string of length n such that it consists of lowercase vowels, which are the following letters: A, E, I, O, and U. We need to construct a string of length n using these letters such that the amount of palindrome subsequences in it is minimized. Now first let's try to think how we can minimize palindromes of lower lengths. Like if you think about palindromes of length 1, you just simply cannot minimize them because any string of length 1 is of course a palindrome because there is just one letter and it's equal to itself. So we can next try to think how we can minimize palindrome subsequences of length 2. Well, in order not to have a subsequence of length 2, we just need to have distinct letters. If there are no equal letters in the string, we of course won't have, because a palindrome of length 2 is when the first letter is equal to the last. So for all n up to 5, we can actually just keep using these distinct letters until, in the case of n equals to 6. Now when n here equals 6, we have to add the second occurrence of some letter, right? Let's say A. One thing you can notice here is when you do this, you create some irrelevant palindrome subsequences. For instance, in here you have A, E, A, I, A. So basically in between these two A's, there are other letters, and you can use them to connect these two A's and make new palindrome subsequences. However, if you group the letters together, so if you use A, E, I, O, U instead, then those two A's will create only one palindrome subsequence, which is just themselves. And of course, you can't do anything about this because they are the same letter. Right, so one thing you can actually notice here is it's always good to group the equal letters together. This is always the optimal order. If you want maybe a more formal proof of this, you can just say, in order to form a palindrome, I need to start and end with the same letter. Now when I have some A's in here, some amount of A's, some amount of E's, I gotta start and end with the same letter, and in order to form a subsequence, what I can do is I can add letters that are in between the start and end. But as you notice, if you fix, for instance, the start to this A and end to this A, in between those two A's, you don't have any other letter than A because the letters are grouped. So you can't form any palindrome subsequence that has kind of like distinct letters, so it's not the same letter. With this move, you actually make sure that you have 0 palindrome subsequences that has at least 2 distinct letters. And when the palindrome subsequence consists of just 1 distinct letter, then you can't do anything about those, because if you change their order, it doesn't matter because it's the same letter. Like, it doesn't matter which one comes first because it's all A's, right? So this is why it's always better to group. More formally, you can prove like this. So now the only question left is how to know how many A's to use, how many I's to use, how many O's, and how many U's. This is the only question left. From here, you could have logically understood, well, okay, I can just repeat A, E, I, O, U, right? Because your goal initially was to like have as many distinct letters as possible. So you can just do this and until you run out of space, so you fill all the letters, and then just sort this array, which will automatically group the letters together, and then output it, which would have been the correct solution. But let's try to understand this more formally, why this is accurate. So basically, in a more simple way, what I'm saying here is, imagine if currently you have 2 A's and 1 E. Basically what I'm saying, it's better to add another E next to this one rather than add another A next to this 2. And you can once again logically understand why this is true, because when you add this A, it creates more palindrome subsequences. Itself, the one with this A, the one with the other A, and when you take all of them together, this is a palindrome subsequence of length 3. So this actually creates 4 palindrome subsequences. And it's of course like not accident, it's just 2 to the power of 2, because there were 2 letters before. And with the same logic here, it would create, when you add the second E, it would create 2 to the power 1, which is 2. And you can see that it's true itself and with the other E. So this creates actually just 2 and this creates 4, right? So you see that adding E would have been better. This is what, so yeah, it's not hard to logically see that you want to balance the amount of letters for each of them. So like the amount of A's needs to be as close to the amount of E's, I's, O's, and U's as possible. If you want to prove this more formally, suppose you have X A's and X E's. In this case, you will have 2 to the power of X palindrome subsequences. The same thing here, because every single subsequence is a palindrome, because like you have X A's. It's all A's. No matter what you choose, your entire substring will just consist of A's and it will be palindrome. So in total, if you have X A's and X E's, you will have 2 times to the power of X, which is 2 to the power of X plus 1 palindrome subsequences. Now let's assume we take one A and add another E, right? So now we get X minus 1 A's and X plus 1 E's. In this case, we'll have 2 to the power of X minus 1 plus 2 to the power of X plus 1. Now before we just had 2 to the power of X plus 1. Now we have 2 to the power of X plus 1 plus some positive number, which is 2 to the power of X minus 1. So it was better before, it was minimized before. And with this same logic, we can generalize this and say that whenever we take from max, so like we have 2 letters and one of them occurs more in the array than the other, whenever we add 1 to this max and subtract 1 from the mean, and if they are equal, of course we can choose any of them to be the max. This is always gonna be not optimal, right? This is always gonna make our answer bad. Now with this proven, we can actually say that when we construct the array in a way that all letters appear equal amount of times, or maybe like the last 2, we just didn't have enough, the n was not enough to like add 2 for each, so obviously you can't always have completely equal, but it's as balanced as possible. That's the point. With this proven, we can actually say that this is an optimal construction, because we've just shown that from this optimal construction, we can never make the answer better. So no matter which one we take, give it to the other, we'll always keep making the answer worse. Now, once again, this is not a super strict proof, but this is div2a problem. So I think this is a good enough proof for div2a, and we understand that most participants didn't even try to prove this and logically understood the solution. Now we can move to the next problem, which is B1. In this problem, we are given a one-dimensional line where we have points from 1 to n. This is 1, this is n. n is smaller or equal than 10 to the power of 9. Now here we have 2 teachers, this is the easy version, and 1 student. In the easy version, we're basically like somewhere on this line, all of them have distinct coordinates. Somewhere we have 2 teachers and a student, like teacher 1, teacher 2, and student, right? Now here is what happens. In each move, the student either stays at the same position or moves to an adjacent cell. So either moves to left or to the right cell. And then teachers move as well. They kind of like coordinate with each other to act optimally. And once again, just like the student, each of them chooses independently whether they stay the same cell, go to the right or left. So one of the teacher can actually go to right and the other can stay at the same place. That can work out as well. Both teachers and student act optimally. What does this actually mean? A student is caught when at some point the student is located at the same cell as one of the teachers. So acting optimally means the student tries to move in a way that will make him get caught as late as possible, and the teachers move in a way and coordinate with each other so that one of them can catch the student as early as possible. And now your job is to say if they all act optimally, how many moves it will take for the teachers to catch the student. Well, in this kind of problems, you can always use the fact that you have very limited amount of people. You have only 3 people, so you can just look for all possible arrangements of these people in between them. And to make it simpler, you can notice that you don't actually need to look for all possibilities because changing the position of the 2 teachers doesn't do anything, right? So you can ignore these changes. Your goal is to just understand relative to the teacher's position, where is the student? Because if you swap the teachers, nothing will change, of course. They work with each other. And with this in mind, we can actually just check 3 cases. The first one is this, when the student is right to both of the teachers. This is our first case. Now, the second case is when the student is to the left of both of the teachers, teacher 1, teacher 2. This is the second case, and the third case is when the student is in between the teachers, right? These are all the cases. Okay, now let's try to consider the first case. In this case, obviously the student will just go to right because the student knows that both of the teachers are to his left, which means that if he goes left, he will get caught earlier. So the student will try to run to right, and eventually the student will stop at the very last cell, which is N, because there are cells from 1 to N, so you can't go off the grid. And it's of course optimal for the student to wait there because that's the rightmost place and it will take more time for the teachers to get there. We can actually even ignore teacher 1 in this case because we see that teacher 2 is closer to N, so teacher 1 can't help in any way. Which means that the answer in this case is gonna be N minus teacher 2. Similarly, in the second case, now the student will run to left and stop at cell 1 because that's the leftmost cell and wait there. And now in this case, teacher 1 is actually closer. So we'll have to output just teacher 1 minus 1 in this case. Now the third case is the trickiest one. But I still think in the example we gave you the answers to all of these 3 cases, so I don't really believe that this problem is pretty hard for B. It even used to be harder, but we made it easier because testers struggle with it. Okay, so in this case, what we can actually do is let's consider the middle cell, right? So basically the cell, like more formally said, let's consider the cell teacher 1 plus teacher 2 divided by 2. So like the cell that is in the middle of them, right? Now, if the student is in between them, we are saying that the student needs to always go to this middle cell and just wait there. Now, obviously, since the student is in between the teachers, the student can always reach the middle cell before any of the teachers. And why is this optimal? The reason is actually pretty simple. We know that both of these teachers can reach this middle cell in some amount of moves. Now, suppose the student moves to right. Now, we know that teacher 2 can actually reach this cell earlier because it's closer to teacher 2 than to the middle. And similarly, going to left would have resulted in teacher 1 reaching the student earlier than teacher 1 would have reached if the student was in the middle. With this in mind, we can actually notice that it's optimal if the student stays in the middle. And for this, the answer is just basically teacher 2 minus teacher 1 divided by 2. Because this is how many moves it will take for the teachers to reach the middle. And yeah, basically this is it. You just needed to understand these 3 cases and how to solve them. Now let's see what B2 says. In B2, there are actually 2 changes. The first one is instead of 2 teachers, now we have m teachers. And m is, let me check, 10 to the power of 5. Besides this, it's also not just one position for the student, but you have q queries on the student's position. And q is 10 to the power of 5 as well. Now, how we can solve this version? Well, first let's try to concentrate on what happens when we add more teachers. So let's ignore the queries for a second to see how fast we can actually answer. Because basically what queries does is it's saying you gotta be able to answer as quick as possible. Like you can just do ON, right? So first let's ignore the queries part and say we have m teachers, what we can do. Well, first we can obviously sort the teacher's coordinate just to make it more comfortable for us, like to visualize it. And all of these are teachers, right? Now we know the student is actually located in somewhere, right? Let's say the student is here. Now one thing you can actually see here is basically all of these teachers are irrelevant. It's once again, you can bring this down to B1 because like you know that those 2 teachers are the ones that have the potential to catch the student. All others are far away. Similarly, if it was like this, the only optimal teacher is this, and the student was here, the only teacher is here, right? So basically what you need to do here is you just simply need to know who is right, who is located, who is the first teacher that is to the right side of the student and who is the first teacher that is to the left side of the teacher. You can ignore everyone else. And in this case, if there is no one to the right, then you just only consider the left. Another question is, can you actually find this quickly? And of course you can. You can just simply use binary search. Because you have some sorted numbers, which are the teacher's coordinate in this case, and you have the student's coordinate, and you need to find in your array what is the first number or teacher's coordinate that is bigger than the number we have, which is the student's coordinate, right? So this is just classic binary search. So with this, we can actually find the neighbors of the student, and after this, we just bring the problem down to B1. Because now we only have the student and the 2 teachers, right? We find these 2 teachers and we ignore the rest. And with binary search, we actually are able to answer in just log. So now when we bring the queries back, it's no problem for us because the time complexity will simply be q times log, which is of course acceptable. This was for B2, pretty simple move from B1 to B2. Now let's move on to problem C. Problem C has a pretty complicated statement. I try to make it as simple as possible, but still, my guess is some people struggled with it. Okay, in problem C, we are given n strings of length m. N and m are both up to 10 to the power of 3. And we are also guaranteed that the sum of n times m over all test cases does not exceed 10 to the power of 6. This just basically means we can comfortably write a solution with complexity of n times m. Okay, so what happens in this problem is actually, once again, we have some n strings. And there are two players, basically. The first player chooses some of these n strings. So it chooses some subset. It can be empty as well. Or like he can choose the first and the last, first, fourth. So basically any subset. After choosing some of these strings, what happens is you just simply put these strings next to each other to form a bigger string. And you put them in order, right? So you first put this, and right next to this you put this string, so you just get a bigger string. Of in this case, if both of them are length 5, then you get a bigger string of length 10. So basically you choose some subset and form the bigger string, which is, let's say, this. The first player does this. Now next, what the first player does is he chooses he always has to like basically find this string, and I'll explain the way of doing that. So the first player initially starts to move from left to right on this bigger string, and the player initially searches for this letter n in this string, right? So if this first one is not n, then he just moves to right. And let's say this one is n. If this one is n, then the player moves to a, right? So basically, the first player is trying to find the letters of this string inside this bigger string, right? So after finding n, then the player will go to the third one and see if this is a. If it's not, we'll move to fourth. If this is not a as well, we'll move to fifth. And let's say this is a, then you'll try to search for r. And let's say this is r, right next to one is r. Then he moves to trying to find e. And once again, let's say the next one is e. Then he tries to look for k, and once again, let's say the next one is k. Now, after he finishes finding all of the letters in this string, he adds 5 to his score. So score 1, which is the score of the first player, you add this by 5 if you find all of the letters. And when you do this, you don't actually stop. So you come back to n again, and you try to search for n. This is the last one. Let's say this last one was n as well, right? And you find the n. But now your big string ends, so you have nothing left in this string. In this case, you don't add anything to your score. And in fact, you don't even consider you have taken this n, because you take the letter if you fully complete this string, right? So if you were just able to take only the first letter, you don't add 1 to your score. You only add 5 if you fully complete the string. So basically this n is just here and nobody took it. Then what the second player does is actually the second player goes through this string, and for each letter that is present here, so N, A, R, E, or K, that the first player failed to use, the second player adds 1 for each of those letters. For instance, this last one, for this last letter, the second player would have added 1 because it is N and the first player failed to use it. Additionally, imagine if this first letter was R. We were not able to use this R because initially we were looking for N, right? Not for R. So the second player would have added 1 for this R as well. So we get some score 2 and score 1. And basically our goal is to maximize the value of score 1 minus score 2. This is what we need to do. So make sure the first player gets the difference between first player score and second player score is as big as possible. Okay. Now, one thing you can, of course, notice here is if you take the empty subset, both of score 1 and score 2 are 0. So you can always have the 0. The answer is always going to be positive, obviously, because you always will have the option to choose the empty subset and output 0. One very important thing to notice here, in my opinion, is to understand that if one string ends with, for instance, NA, eventually what would logically happen is you wouldn't be able to use this, so you would stop at A, and you wouldn't add anything to your score. And the opponent would have added 2 for both of these letters to their score. So even though for this individual string it might not be correct to take it, maybe the next string starts with R, E, K. Now in this case, those two connect to those 3 to form the string, right? So in this case, not only the opponent loses these 2 and these 3, so opponent score is reduced by 5 if you combine these 2 strings together. You also add your score by 5. So in difference, you actually gain 10, right? Because you add 5 to your score, and your opponent loses all of those 5 letters. So this actually means that you gotta consider combining strings to take advantage and not look at the strings individually. If they are optimal, then take them, right? And this actually hints you to use dynamic programming approach. Basically, what we've done here is when considering to choose this string, we've said, okay, what if before this I have ended on the letter A, right? So basically, I'm saying, let's say I've ended on the letter A. Let me try to continue from searching for R. This is basically what I've said. So basically, what we can keep in the dynamic programming is dp0 showing we are looking for N right now. So we're looking for the 0th letter on this string, right? Which is N. We're numerating from 0, let's say, right? So we're looking for N. dp1 similarly would have mean we are looking for A, dp2 for R, dp3 for E, and dp4 for K. So dp4 means we're looking for K. Okay. So initially what we need to do, obviously, is we can say dp0 is 0, right? Because the difference between scores currently is 0, and we can start by looking for the letter N. However, all other DPs, like dp1 to dp4, need to be some very big number, like let's say int max, because you cannot yet start by looking for A. Maybe if you start for looking for N, you can end up in some place where you need to look for R. In that case, you can update the corresponding DP, but initially you can't update that because according to the rules, you gotta start looking for N. Now after this, what you can do is for each string, right? By the way, I think I forgot to say, dpi basically shows best answer, which is in our case the max answer, max difference. such that we're looking for the it letter currently. So whenever we're moving to the next string, what we can do is we can brute force on what letter we're currently looking for, from N to K. Obviously, first check if the DP is not int max. So before this, we have reached that letter, right? If it's not int max, then we can try to continue on this string from that letter. So initially, instead of looking for N, look for R, for example. And we can, of course, in just OM, M is the length of the string, find out what result we'll get if we take this string and we continue from some letter. Obviously, at the end, you will get to some letter. So what I mean by this is you take R, you take E, you take K, maybe add score by 5, and then take N, A, and let's say you take R as well and the string ends. In this case, now you know you came to E, which is, in our case, DP3. So you can update DP3 by max of DP3 in case we had a better answer. In case we had a better answer when we are looking for E, or initially, let's say you were at DP1 before the string. So by DP1 plus new. Now new is just the new score you got by taking this string and looking for the letter A, which is just showing the DP1, right? And DP1 is just the past answer we've gotten to reach the first letter. So basically, you update your DP3 by this, because you know if you started from the first letter, you would have reached to the first until the end, and you also counted your score new. This is basically the main idea, and at the end, what you actually need to output is dpi minus 2 times I. Now, why 2 times I is actually simple. I mean, it kind of depends on how you counted dp, but in most cases, you need to output like this, because basically what, for instance, dp1 shows is the answer if you are currently looking for the letter A, right? So this means that you've already taken one letter, right? But remember, according to the rules, you add to your score only if you finish the entire string. So you add 5 if you finish finding all of them, right? So if you find all of these 5 letters. But if you are currently at A, you can't add it to your score for this letter. However, you kind of need to add when counting the DP, because you don't know, like maybe you will find this AREK in a string that comes later, right? So you kind of need to add this N initially, because you don't know if you will end on this N. This is why here, if you end on this, you need to subtract this one letter from your score and also add it to your opponent's score, right? So you remove this one letter from your score and add 1 to your opponent, which in total gives a difference of 2, which is just 2 times 1. That is why you you subtract 2 times I. And remember, dp0 would have been if you are currently looking for N. So you've completed the entire thing, which is NARAK. So in this case, I would have been 0, and you would have just outputted dp0, and you wouldn't have subtract anything, because 2 times I would have been 0. So yeah, we actually see that this is actually correct. This was it for problem C. Now let's move to problem D. In D, we are given 2 arrays. The first one is A1 from AN, and the second one is B1 to Bn. Pretty standard constraints. N is like smaller than 2 times 10 to the power of 5. A's and B's, all these numbers in the arrays are up to 10 to the power of 9. And what we can do in this problem is we can perform the following operation at most once, or not perform at all. And the operation is the following. We can choose L and R, and for each I that is smaller, that is in between those L and R's we have chosen, so choose some continuous part of the arrays, right, in a more visual way. And for each number that is in between the continuous part you've chosen, you just swap AI with BI, right? And after doing this, you need to perform the operations in a way such that GCD A1 up to AN plus GCD B1 up to Bn is just maximized. So your goal is to maximize this. All right, let's see how we can do this. We actually have a lot of solutions for this problem. Some of them are more logical than the others, but I'm gonna explain the solution that is probably the simplest and most beautiful, and I'll try to, like, in a short way, also explain a solution which can also kind of prove why the first one was correct. So the way we can actually solve this problem is we can say, all right, let's move from left to right and check prefix GCDs. Let's say we have prefix AI, which is just a prefix GCD of array A, and we have prefix BI, which is the prefix GCD of array B. Now we move from left to right, and for each I we check if prefix AI doesn't equal to prefix AI minus 1. So if the prefix GCD of array A changed, or prefix B I does not equal to prefix B I minus 1. So if the prefix GCD of array B changed, right? If any of this happened, then what we do is we can actually fix L to I minus 1 and then brute force on R. Now, this is actually the full solution. Let's try to understand why this is good in terms of time complexity and why this is correct. Now, first I want to talk about this brute force R. It's pretty simple how you can actually do this. If you have your L fixed, then you can brute force R because, like, this is your L. You just brute force R in ON time complexity, and along this way, you just count the GCD of this part, right? And you also initially, before all this, counted the suffix GCD and the prefix GCD. Now, when you brute force on R, all you need to do is you need to check what happens if you swap those middle parts, right? And since you, along the way of increasing R, you counted what is the GCD in between, the prefix GCD, the suffix GCD, you can easily exchange those two parts and see what the new GCD becomes, right? Okay, now let's work on the second point, why this is not time limit. The reason why this is not time limit is because we do this ON brute force when the prefix GCD changes. The prefix GCD can only change log amount of times at max. Because, like, imagine if you have some number, let me write here. If you have some number, the best you can do the GCD is always going to be a divisor of this number, right? And if it says 12, we are not doing anything. So it needs to go to its biggest divisor, which is the best dividing it by 2, the smallest possible number. 6, and then you can go to 3. So basically what you're doing is the best you can do is to just keep dividing by 2 to change the GCD, because the perfect GCD is a divisor of the first number. So you can only do this log amount of times, which means that we actually, this condition was true only log amount of times, and we can actually easily do O(n) time complexity for log amount of times. The total will just be n times log. Or I mean, we're doing or, we're checking for both of them, but you can ignore the constant because it doesn't really do much. Like it would just be 2 times n times log. Okay, so now let's try to understand why this is correct, right? For this, I want to talk about a more kind of like a solution that is easier to understand why it's accurate. Let's say instead we fix the GCD of the first array and the GCD of the second array, right? So there's some GCD A and GCD B. And you can actually fix this because the GCD is always a divisor of A1 here and divisor of B1 in here, right? And those numbers are like, the numbers can have like up to 1000 divisors. The numbers up to 10 to the power of 9 can have up to 1000 divisors. So you can actually fix them. It will be just 10 to the power of 6. But time complexity here doesn't mean. I just want to use this fact to help you understand why the solution above was correct. So why you can only look if the GCD changed. Let's say we fixed our GCD A and GCD B. Now the way we can actually solve this problem is we can say, let me find the maximal index in the array I such that the prefix GCD here is actually divisible by GCD A. So divisible by GCD A. Now one thing I know is if I add just one more number here, just one more, it won't be divisible by GCD A anymore. So I cannot achieve GCD A in the first array. Similarly, let me find the lowest index such that the suffix is divisible by GCD A. Now when I do this, one thing I know, in order to achieve GCD A in the first array, I need to change this part in between. I have no other way, I'm forced to change it. Similarly, we can do this in the second array as well, and let's say we get something like this. So now I know I need to change this part and this part, right? So in total, I need to change those parts, right? In both arrays, I need to change those parts. The minimum of both left points and the maximum of both right points, basically. So I can just change this part and see if I get GCD A in the first array and GCD B in the second array. If I get, I achieve my goal, right? This is another way I could solve the problem. And it turns out this is actually pretty similar to what we said above. And what we said above is actually faster than this. Not by much, but a little bit. Now, basically what we were doing above is, imagine if we have the following array. We have 6, then we have 3, and let's say we have 2. Now, for instance, when we get to this 2, what we will see is that GCD becomes 1, right? The GCD of 6, 3, 3, 2 is 1. So we see that the GCD changed before because the GCD was 3 before. So what we do is we just set L to I minus 1, which is this 3, right? Now, if you consider the solution we set above, basically what we are doing here is we are fixing the GCD to be 3, and we are fixing the GCD to be 3, and like we are just choosing the last number such that the GCD is 3, right? That's what we are doing above. And basically, we are kind of doing the same thing here, but in reverse. Because once again, if you look at this, we'll look at all cases we looked above, right? Above, if let's say we fixed the GCD of A to be 3, what we would have done is we would have found the biggest index such that it's still 3, and it would have been this, right? So we wouldn't look for anything else. And basically that's what we are doing here. We would have also fixed this, and right, so because like it's the first number, so before you had no GCD and now GCD is 6. So this is also considered a GCD change. So you also fix this. So in a way, you kind of like fix all left points and consider all fixed GCDs as well in this solution. That is why this one is correct as well. This was it for problem D. Now let's move to problem E. First, I'll explain E1. Okay, here is what you have in problem E1. We are given some matrix and we're given some array. Array has some numbers and the matrix has some numbers as well. Let's say like this, and some other numbers here that I don't care about for the moment. Basically what happens here is two players play a game. The first player tries to search the first number in the array inside the matrix, right? Let's say they find it here. Obviously, it can appear in the matrix more times, so they can choose whichever one they want. In this case, there is only one. So let's say they choose this one. Now, when they choose the cell at 1, 1, the next player needs to choose, or for more general explanation, let's say ij. And I and j are both 1 in this case. The next player needs to choose, basically the second player needs to choose the second number in the submatrix starting at I plus 1, j plus 1 and ending at nm, right? So they need to choose 4 in this submatrix, which is once again the very first number. So the second player would choose this. Now, the first player needs to choose the next number in the array inside the next sub matrix, which is this one that I've just highlighted. And here they can actually choose this 5. And when they do this, now the next player needs to choose this 6 inside this sub matrix. And they can actually do this. Now, the question is who wins? Well, there can be multiple possible outcomes. Obviously, first, the player might not find their current number, so they need to search for numbers in the array. Maybe they can't find that number inside the matrix. In this case, that player loses because they can't find their number. The second possibility is when the matrix ends, right? If I equals to n or j equals to m, then the matrix ends because I plus 1 will already be out. In this case, the player also loses because they have an empty matrix and they can choose anything in it. The next possibility is what happened here. The player chose the last number of the array and managed to find it, and now there are no other numbers in the array. So in this case, the first player loses because they don't have anything else to find and it's their turn. These are basically all the possibilities, and your goal is to find who will win the game if both players play optimally. In the easy version, L and M are both smaller than or equal to 300, and all numbers in the matrix and array are smaller than min 7 n times m. Alright, now let's see how we can solve this. Well, E1 can actually be solved in a very simple way. Let's say dp I j k shows if the first player can win if the game was to start from kth index of the array instead of first, and we considered the submatrix starting at cell ij and ending at nm, right? Instead of from 1, 1 to nm. So this is true if the first player can start from these conditions and win, and it's false if the first player will lose. Now, updating this dp is once again very simple, because we can check if starting from the next subrectangle and from the next index of the array, we would have lost. Now, if this is losing, so if this is false, then we can assign true to this, because we know that we just choose the cell at ij, and we will give this position to our opponent, which we know is losing because it's false, right? So this is how we update the dp, pretty simple. And at the end, what we just need to do is we need to say, okay, if for any ij, we can just brute force on i's and j's. If for any ij, dpij 0 is true, then the first player wins. Otherwise, the first player loses, because they start from the first index in the array, and the first player can choose to pick up any cell with coordinates ij on their first move. So if picking up any of them and starting from the beginning of the array ends up winning for the first player, then first player wins. Otherwise, for any possibility, the first player is gonna lose. Now let's move on to E2. Now, one hint we have given here is this. This is actually an important constraint that can help you to make an important observation in this problem. What is that observation? Let's say we have some numbers in the array, and eventually some of the numbers, let's say the 2, appears for its second time. Now, what we are saying is actually we can just consider this array, and no matter how many things come after this, we can ignore. Let's see who wins if we consider only this part of the array, so these 4 numbers. Whoever wins on this array will also win on the entire array, no matter what came here. This is the observation. Now, why is this true? Let's try to understand that. Let's say in our matrix we have some 2's. Now, obviously, if we have no 2 in the matrix, then whoever gets this 2 will lose immediately, so we don't even have to consider that case. Now, we know there are some 2's in here, right? 2. And then maybe inside this there is another 2, right? And there are 2 possible cases. Either the person who wins here gets to the 2 first, gets to these 2 first, right? So either the winner gets to these 2 first, or the loser gets to these 2 first. And by winner and loser, I mean the winner and loser if we're only considering this yet, right? Let's say the winner gets to these 2 first. Now, if the winner gets to these 2 first, then the winner will choose the 2 that doesn't have 2 in its subrectangle, right? Now, imagine if the winner chooses this, then the winner gives its opponent access to all these squares, right? To all these squares. However, if the winner was to choose this, then the winner gives opponent access to all those squares. So by choosing the 2 that doesn't have 2 in its subrectangle, you are actually limiting your opponent's moves. So it can never be bad, because if choosing these 2 would have resulted you to lose, then choosing the other 2 would have resulted you to lose as well, right? So basically the winner would have just chosen the last 2, so that when they get to these 2, the other person won't be able to choose it. The next case is when the loser gets to the first 2, right? Let's try to understand what happens in this case. Now we know that the winner wins regardless of what the loser chooses. So even if the loser chooses these 2, we know that we can still win, because we win regardless of what the opponent chooses. So even if the opponent chooses these first 2, we'll just respond by a move inside this to make sure that there are no other 2s, right? Because we know that the opponent will need to look for these 2, right? Because for the second 2, because we know we are the winner if we cut away from that part. So if we are the winner, it was the opponent's move to choose the second 2. And we also know that if the opponent was to choose the very last 2, we could have still beaten them by replying with something that is inside this subrectangle of the last 2. So we can just make our reply inside here, no matter which 2 our opponent chooses, and still win them, and they won't be able to find the 2. So basically we've just proven that we can cut the array off from this part. And what this does, of course, you could have coded in E1 instead of n times m times LDP, you could have coded n times m times 7. However, in E2, actually, the constraint is that the numbers are smaller than equal and then n times m are smaller or equal than n times m. So we can't do the same thing here, because n times m is like more than 10 to the power of 6. And obviously we can do 1500 times 1500 times 10 to the power of 6. But actually still cutting the array off is pretty important, because now we know that each number appears only once in the array. So each number has a specific index in the arrays, and this fact is pretty useful in trying to optimize our dynamic programming approach. So basically we need to get rid of this L in our dynamic programming. We need to come up with some dpij simply, right? Here's how we can do that. Let's say dp0 ij is equal to the least winning even index in our array. And obviously this ij doesn't change. This ij just means we are considering the subrectangle starting from ij to nm, right? So what is the least winning even index? And similarly, dp1ij is just odd index with this exact same definition. It just even is replaced by odd. It turns out this dp is actually sufficient to solve this problem. We update dp in the following way. Let's say we are currently looking for the cell with coordinates ij. In this case, to update dp0ij, what we can do is, let's say this is our ij, the top and the leftmost one, right? So if we were to choose the cell there, then the opponent needs to reply us somewhere in here, right? this highlighted part. And they can actually choose any of these. And one thing you can actually understand here is I'm gonna basically tell you how to update both dp0ij and dp1ij, but you obviously don't need to update both, because if at cell ij you have a number that appears at an even index in your array, then you need to update dp0 because it appears at an even index and each number appears once in the array. And if it appears at an odd index, then you need to update your dp1, right? Now, let's assume that the number in this cell appears at an even index, so we're trying to update dp0ij. Now we know if we choose this number, our opponent needs to choose the next number in the array which has odd index. So the other opponent basically needs to choose some dp1 in this, right? Needs to fix some ij that is inside this subrectangle and choose the dp1 ij for that. Now let's say, what is the minimal dp1 ij inside here? Let's try to understand that. Basically, what I'm trying to say is, if one of the dp1 ij's, let's say dp1 min. Let's say dp min actually. What I'm trying to say is, if our dp min equals dp0 ij plus 1, then this means that our opponent is gonna win. Why? Because we know that, actually, instead of dp0 ij here, I meant like where this number appears. dp0 ij is some number and it has some index, right? Some index 0. This is the index of like basically the number written on the ith row and jth column. Where does this number appear in the array? What is its index in the array? Right, so array index. And here, if dp min equals to idx 0 plus 1, then it actually means that we don't need to do anything, because and like we update it if we see that it's a winning state. So dp0 ij is a winning state. Then we update it by the least possible index. But this means that it's not a winning state, because we see that our opponent has a dp which in the subrectangle that is valid, which is winning for the next index. So if we reply by idx 0, our opponent has a winning reply that is to choose some idx 0 plus 1 in the subrectangle, right? Now the question arises, in what cases can we update our dp? Those are the cases when dp min is bigger or equal than idx 0 plus 3. Because now we know that the least index such that the opponent will choose it and win is actually not the next index, but is like if we are choosing this is the opponent's reply, this is our reply, and this is the opponent's reply. Now this is idx 0 plus 1, and this is idx 0 plus 3. Now we know our opponent's reply to this that is winning is this, and it's the least possible index that the opponent will win. So we know that our opponent has no way to reply to us by the game rules, which is to choose the next number in the array that is a winning state for them. Now that means if we take our current ij, then we're gonna be winning. And this means that we can actually update our dp0 ij by idx0. So make this equal to idx0, because this is a winning state for us. If this condition holds, of course. And if the above condition holds, this is not a winning state for us. And with the exact same logic, we update dp1, but now we use dp0, because if we choose an odd, then our opponent needs to choose the next, which is even. Okay, now the only question left is what do we output at the end, which is also pretty simple. If at the end we can just look like, let's consider the dp0 ijs. And if any of this equals to 0, then the first player wins, so you output t, which is what you need to output if the first player wins. Or if there is no ij such that this holds, then you output n in any other case. Because if this holds, once again, according to our dynamic programming definition, this means that this is a winning start. So if we start from index 0 and consider the subrectangle of ij from n to m, then we win. And obviously the first player can choose whichever number they want. So they can kind of choose which subrectangle to start from, right? The only thing you need to make sure is that they can win if they start from the beginning of the array, which means that it's just equal to 0. Now, if this holds, then you output t. Otherwise, the second player wins. And yeah, this was basically it. This is how you could have solved problem E2. Initially, we had E1. Like in E1, we wanted you to make this observation. Where is it? Yeah, this observation that you can cut the array off and do like n times m times 7. That is why initially the numbers were like 1000 and not 300, but we realized that testers are struggling to make this observation, so we made E1 much easier, which is just simple n times m times LDP. This is it for the editorial. I hope the solutions were clear to you. If you have any other questions, feel free to ask it, and feel free to also leave feedback regarding the round. I hope you enjoyed the round. This was it for the video, and we're looking forward to seeing you in future rounds.